In this problem, we're asked to sketch the magnitude characteristic of the Bode plot for the transfer function h of j omega is 5 times j omega plus 10 divided by j omega times j omega plus 100. Our first step is to convert to standard form so that we can use our straight line approximations. So in doing that conversion, for instance, we'll divide or factor out a 10, so we'll have 5 times 10 times 0.1 j omega plus 1. And then in this term's in standard form. To convert this one, we need to factor out 100. So we'll have j omega times 100 times 0.01 j omega plus 1. And if we look, here's 50, and so we have 50 and we have 100 in the denominator. So h of j omega then is 0.5 times 0.1 j omega plus 1 over j omega times 0.01 j omega plus 1. So if we look, we have a gain term. We have a simple 0. From this term, we have a pole at the origin, which is this one. Then we have a simple pole. Okay, the 0 is at omega equal 10 radians per second, and the simple pole is at omega equal 100 radians per second. So now we'll go through and look at the characteristic of each of those, then we'll add them all up to get the plot, Bode plot, of the magnitude characteristic of this transfer function. So if we look, our gain term here is a 0.5. So if we do a plot of that as a function of omega, we can see if we convert it to dB, we'll have 20 log base 10 of 0.5, which is minus 6 dB. So our characteristic for our constant term is just a value minus 6 dB for all frequencies. Okay, next is our pole at the origin, and if we refer back to the textbook, the gain characteristic for a pole at the origin is shown here. It has a slope of minus 20 dB per decade, and at omega equal 1 it has a gain of 0. So there's the pole at the origin. Then our simple pole at omega equal 100 looks like this. So the straight line approximation has a gain of 0 out until omega equal 100. At that point it turns down at a rate of minus 20 dB per decade. And then for our 0 at omega equal 10, it has a gain of 0 out until omega equal 10. At that point, it turns up with a slope of 20 dB per decade. So now we're going to sketch the characteristic. There's the ones of all the terms individually. Now we're going to add all those together to get the expression for the magnitude of h. Okay, so we plot an omega in radians per second, and we have a log scale. We're going to plot the magnitude of h in dB. And let's go ahead and label, for instance, here's omega equal 1. This is a reference point for our pole at the origin. Here's 10, and then here's 100. So if we think about it, our gain characteristic for our pole at the origin, it has a value of 0 dB at omega equal 1. But if you remember, we have this constant in here that has a gain of minus 6 dB. So if we look, for instance, at minus 6, then our curve should pass through there at minus 20 dB per decade. Okay. And as it continues on at minus 20 dB per decade, our 0 at omega equal 10, from omega greater than 10, it's going to turn up at 20 dB per decade. So we continue down at minus 20 dB per decade until a 0 comes on. At that point, it's going to our curve's going to flatten out. Now, if we remember, here's a whole decade of frequency between 1 to 10. So this is going to be minus 26, because in going from 1 to 10, that's a decade of frequency. We know we're at minus 20 dB per decade. Okay, the characteristic is flat until we get to 100. At that point, that pole begins to break off at minus 20 dB per decade. So the characteristic goes like this, and the slope here is minus 20 dB per decade.